the first important piece of information we have is that it's moving vertically at a constant acceleration. This tells us that we can use the kinematics equations. Okay. First, let's draw a picture. So if we have a pendulum of length b attached to a mass m, and it's moving vertically with some constant acceleration. If we're to draw a coordinate system, we have our x and y. And if we redraw the pendulum, we could form a triangle. So this is our length b. We have x and y. Forgot to draw the angle theta. Now if we solve this triangle for x and y, we have x is b sine theta, and that's positive. And then for y, since we're using the kinematic equation, that's simply 1/2 acceleration times time squared plus v naught t minus b cosine theta. And that's from this component, this side. Now, since we want kinetic energy, we need to find x dot and y dot. Well, x dot is just b theta dot cosine theta, and y dot is b theta dot sine theta plus acceleration times time. Since the system starts at rest, we can set this term to 0. Since there's no initial velocity. Now we simply plug in x dot and y dot into our t equation. Now for our potential energy, it's just mgy Now one thing that you'll want to do is set your 0 for your potential energy. And for that, I'll do it right at the x-axis. So this is where I'm grounding the potential energy. Now we can write the Lagrangian, t minus u. Now we're going to want to FOIL out this term here. Okay. And then I'm just going to distribute this negative mg. see here. So in this term, we could factor out a b squared theta dot squared. And then we're left with cosine squared theta plus sine squared theta. And this, of course, is 1. Okay. Now there's only one dependent variable in this equation, and that's theta. So that's going to be our generalized coordinate. So the Euler-Lagrange equation says that so the first term we'll solve for is the partial of L with respect to theta. And right off the bat, we can see that some of these derivatives are going to be 0. So this term will not exist. Neither will this term. Neither will this term. So if we just rewrite, because those derivatives go to 0, then we'll have 1/2 m 2at b theta dot sine theta plus mgb cosine theta. Okay. So this is our dl d theta. Now we need the other components as well. So if we take the derivative of L with respect to theta dot, let's see if any of these terms go to 0. This one will, it doesn't contain theta dot. This one will, and so will this one. And so this is what we have to take the derivative of. Much simpler. I'll pull out the constant. notice that the 1/2 when distributed cancels out the 2's, and why not? We'll just distribute the m as well. And then the final component, we're going to have to take the time derivative of this. First term is pretty easy, mb squared theta double dot. And then for the second term, we're going to have to use product rule. But first, I'll just take out all of the constants. We have d dt of t sine theta. So using the product rule, we'll get the derivative of the first times the second plus the first times the derivative of the second. And then I'll have to redistribute that out as well. Okay, now we want to set both sides equal to each other, so we're actually going to plug in what we found to the Euler-Lagrange equation. These two terms cancel. And let's solve for theta dot, the equation of motion for theta. I can factor the negative and the sine theta and the b. So rewritten more suggestively, we have this. So this is part A completed. Now we're going to need to do part B, which is to find the period for small oscillations. And the first step is to recognize that for small oscillations, sine theta is approximately equal to theta. So if we rewrite our part A answer, we get theta dot is negative a plus g divided by b theta. Now this looks very similar to the differential equation for the simple harmonic oscillator, which is theta double dot is negative omega squared theta, where the period is 2 pi over omega, the angular frequency. Just as an aside, you don't need this for the problem, but omega is 2 pi f. So by comparison, we could find omega and then plug omega into the period, and then we know the period for small oscillations. So by inspection, we see that omega is equal to the square root of a plus g divided by b. And so the period is 2 pi. I'll just write omega to the negative 1. And the negative will just flip the numerator and the denominator. This is the period of small oscillations. And that's it.